This brings us right back to Lorentz and Einstein. So we return to Einstein in 1907. In 1907, Einstein assumes, quote, the complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system, end quote. And, by doing so, also predicts that clocks dilate due to gravity, and that light should bend in the presence of a gravitational field. He did so by extending the principle of relativity to an object with a constant acceleration. A constant acceleration means that the velocity changes over time. If you imagine a frame of reference which is moving with the object, both of which are moving relative to the stationary frame of reference, we could imagine putting a velocity frame of reference at the location of the accelerated frame for each unit of time. If we restrict ourselves to the small changes in the beginning and set them all together at t equals 0, then after the first click, the s' frame and the sigma frame are now in location 2 together. If we synchronize our clocks in the s' frame, we know by special relativity that for this to be perceived as true for people on s', then people on s will calculate the front clock as being behind in time and the back clock as being ahead in time. After the next unit of time, sigma no longer matches s' or s. When the s' and s' frame calculate the difference of sigma's local time from their perspectives, they find that the local time of the object is equal to the total of the other two times, call it tau, times 1 plus the acceleration over c squared, times the distance from the observer. However, from the point of view of a single object that spans that length and exists in the frame of sigma, it is required to use the time tau, which appears as a normal functional clock to them. Einstein, having already assumed that we cannot tell the difference between being in an accelerating frame of reference and gravity, shows that we can replace the acceleration of the frame and the distance with phi, the gravitational potential, obtaining that clocks above the ground run faster than the clocks on the ground by a factor of 1 plus phi over c squared. Given this, Einstein then proceeds to show that that fact will have an effect on photons, that gravity will affect photons despite photons having no mass. Einstein showed that momentum is replaced by momentum times this factor, and likewise the speed of light is replaced by the speed of light times this factor. Therefore, Einstein was able to show that light rays that propagate with the x-axis are affected by the gravitational field, and that the light rays which do not propagate along the x-axis are bent by the gravitational field. It is important to note here that this does not mean that the speed of light actually changed, but rather that the accelerating frame's spatial coordinates are changing in a curved manner. The coordinate velocity of light changes, not the speed of light itself, which would be strange given that we need that number to calculate the appearance. This has a very important meaning in regard to Einstein's 1905 discovery that mass and energy are related, and that an object in motion appears to change in kinetic energy. More so, this discovery that even photons will be affected by a gravitational field helps illuminate the answers he was searching for. Einstein had previously stated that if you add energy to the object, for example, forcing a magnet near another magnet that it is repulsed from, that gain of energy will increase its mass. Einstein was now looking to show that if that object is a mass and the energy you add to it is caused by gravity, that the result will be the same. Given all of the above conclusions of special relativity, Einstein concludes the paper stating, quote, "This equation expresses the principle of conservation of energy and contains a very remarkable result. To each energy E in the gravitational field there corresponds an energy of position that equals the potential energy of a ponderable mass of magnitude E over c squared. Thus the proposition that to an amount of energy E there corresponds a mass of magnitude E over c squared holds not only for inertial, but also for gravitational mass." End quote. In 1911, in the paper titled On the Influence of Gravitation on the Propagation of Light, Einstein expanded the views he established in 1907, including postulating in the introduction of that paper that one can test his hypothesis by looking for rays of light passing near the sun, and you will find that they are deflected by about 1 second of arc. In this 1911 paper, Einstein shows that the gain of inertia mass from a gain of energy is identical to the gain of gravitational mass from a gain of energy, and that it is in fact the principle of relativity that merges the principle of conservation of mass into the principle of the conservation of energy. Given this, he states that if you send radiation energy from a high position above the ground down to the ground, and assume there is no gravity, but you find a way to accelerate the object to the ground, then, given the special relative nature of clocks and lengths, the energy that the ground receives will be greater than the energy sent. And by that same argument, the speed of light, c, at ground, should appear to be equal to the speed of light on the ground plus the speed of light at a given gravitational potential phi divided by c squared. And, therefore, he writes, quote, "The principle of the constancy of the velocity of light does not hold good in this theory in the formulation in which it is normally used as the basis of the ordinary theory of relativity. That the velocity of light in a gravitational field is a function of place. That light rays propagated across a gravitational field must undergo deflection." Einstein then states how we must model this by returning to a plot where light is constant, and through Huygens' principles of light, we deflect a plane of light by using circles and taking the flat spacetime, and we get the angle of deflection. Einstein then concludes that, quote, "A ray of light traveling past a celestial body undergoes a deflection in the direction of decreasing gravitational potential, and thus in the direction towards the celestial body." Everyone wanted to prove this was either true or false, and given that they had stars and a sun nearby, it seemed pretty simple. First, we just need a solar eclipse, so that the sun does not blind us when we look near it. Then we just need to measure where the stars behind the sun are. Then we wait for the sun to move from in front of those fixed stars and check again in 3 months to see if the relative distance between them changed when there is a massive object between them and us. Well, it was not that easy, because if you do any astronomy, you know that clouds will ruin everything. In October 1912, during the first solar eclipse available, it rained. So they tried again August 21st, 1914, and again, clouds. Then, and you'll know why if you are a bit of a history buff, you'll notice that the next few years of science into the angle of deflection of light caused by massive celestial bodies stopped in order to start working on science for projectile weapons and flying machines and big heavy armored vehicles. In 1916, Einstein proposed 3 tests for general relativity, which subsequently became called the classical tests. The first was that the general theory of relativity properly calculates the precession of Mercury's orbit, predicting an extra 43 seconds of arc in its precession. Second, light will be deflected by the sun. Third, that light escaping from a star or a planet will be redshifted, meaning its wavelength will appear more in the red section of the visual light spectrum. It was already established by 1882 that the measured precession of Mercury was approximately 43 seconds of arc. In May 1919, Arthur Stanley Eddington was able to prove Einstein's second test for general relativity, finding the light from stars of Taurus from behind the sun that had deflected at the angle that Einstein had predicted. Finally, in 1925, results for measuring the star Sirius proved to have been redshifted. In 1959, the Pound-Rebka experiment proved Einstein's gravitational time dilation here on Earth. Einstein's theory of general relativity was also able to predict the cosmological constant, universal expansion, the Big Bang, the cosmic microwave background, black holes, and gravity waves, all of which have been demonstrated beyond a reasonable doubt today. Thanks to these discoveries, global positioning satellites are able to keep proper time on Earth by adjusting their on-board atomic clocks with a special and a general relativistic shift to counteract the velocity and gravitational potential of the satellite and its clocks. If it were not for Einstein's general theory of relativity, any satellite we threw up into space with a clock on it would very quickly become out of sync with our clocks on the ground, and our GPS would tell us to drive into the ocean. If that which Einstein's general theory of relativity predicts does not actually exist, then the global positioning satellites above Earth would have no reason to time dilate. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.